Thank you to everyone who has joined us so far. We're going to give just a couple more minutes for everybody to join us today. All right, thanks for your patience, everyone. We're going to go ahead and get started today. So, welcome. Good morning, good afternoon, wherever you are. Welcome to the Carbon Solutions webinar series, where we're going to showcase some innovative work that we're doing with our partnerships and industry experts. I'm Rachel Esch, and we're excited to have you. So, just to tell you a little bit about today's session, it's going to focus on carbon management with CO₂ transportation. So our presenter, Tracy, will dive into unique challenges and opportunities surrounding CO₂ transport, exploring pipelines, rail, barge, and truck logistics. Tracy's also going to introduce a little of Carbon Solutions cutting-edge software designed to optimize CO₂ transportation strategies and pave the way for carbon management solutions. And just before we get started here, I just wanted to note the session is being recorded. It will be available on our YouTube channel along with our past webinars. And by attending, you will also be added to our newsletter for updates on future events, resources, and webinars. And we encourage you to add any thoughts or questions to the chat throughout this presentation. At the end, we will have time to dive further into that Q&A. And thank you again for joining us. So now I'm going to pass it over to Tracy to get started.
Hi, everyone. I'm Tracy Ziv. For those of you who don't know me, I run our CO₂ transportation projects here at Carbon Solutions. So like Rachel introduced, I'm going to be talking today about the critical link in the carbon management value chain of transportation and some of our opportunities and challenges in that space. So in order to meet CO₂ storage, capture and storage demand in the US, we're expected to need to capture and store between 1 and 1.7 billion tons of CO₂ per year, per the Princeton Net Zero study, which is a tremendous amount of CO₂ by 2050. And a thing is that when you're capturing CO₂ at a source, you might be located somewhere near a suitable storage site, but you might not. On the left, you can see a map from our Concord database that shows all of the CO₂ emission sources in the United States. And on the right, you could see a map from our Scott database, which shows CO₂ storage capacity potential in various areas in the United States. And as you can see, in some areas of the country, for example, along the Gulf Coast or in Illinois and Indiana, there's a large number of emission sources right on top of very high quality, high capacity storage. But in other areas, like along the East Coast, you see that the sources in that area are not close to quality storage sites. So in order for us to be able to meet that carbon management demand of 1 to 1.7 billion tons of CO2 per year, we need some way to be able to get from those sources that are not located near a quality storage location to one of those storage locations. And that's really where CO2 transportation comes in. CO2 is that missing link in the value chain. You can't capture CO2 if you have nowhere to put it, and you can't store CO2 if you don't have CO2. So in order to have those critical pieces that we need to meet the United States' demand for carbon capture and storage, we need transportation. So we've got a map here with an overlay from our SimCCS software connecting various locations with good storage potential and various locations with emission sources. It's kind of a framework for what a countrywide transportation network can look like. And you see that this looks pretty busy. Typically, when we're talking transportation, we're talking pipeline, because at the scale of CO2 that the United States will need to move around in order to meet our carbon capture and storage demand, pipelines are really typically the safest and cheapest option to move those large quantities. But as you can see here, there are some cases where for smaller quantities of CO2, for locations that are remote, not located near other facilities, such that they can't pool their CO2 to have larger quantities with other nearby sources, it can make sense to use another transportation mode, like a truck, a rail car, a barge, a ship. And then there may be other reasons where, for environmental impact or regulatory or political reasons, you may not be able to use a pipeline. And then in those cases, other transport options can be very valuable. And in fact, in some places, we do see limited instances. For example, in Europe, there's a network of shipping of CO2 on the ocean between some European countries. So what the Princeton Net Zero estimates is that by 2050, because in terms of high volume transportation for CO2, pipelines are our best option, that we may need up to 66,000 miles of new CO2 pipeline in the US. This is their map of what they think that scenario looks like. And you can see it's extensive. It covers a lot of the country. So for people interested in transportation, interested in pipeline, there's a tremendous need and a tremendous opportunity to develop this infrastructure. And at Carbon Solutions, I touched on some of our software, but we combine our award-winning software with our extensive interdisciplinary experts to be able to drive solutions to that CO2 link problem of what is the optimal way for a project or an area that you're looking at to take CO2 from emission sources and get it to a CO2 sink and make a project that's economical, that meets environmental requirements and permitting requirements, that's able to be located in a way that takes into consideration social concerns and community concerns for the people living near those projects. So that's really what we do at Carbon Solutions. Our software, SimCCS, is kind of the glue that holds everything together in optimizing these networks of sources, sinks, and the transportation links between them. Our Scott database looks at storage capacities and estimates storage costs. And our Concord database looks at sources of emission, types of sources, sizes of sources, costs to capture from those sources. And our Concord database shows information about the areas where we may be routing and allows us to account for factors like population, topography, environmental considerations, environmental justice considerations, land ownership, existing infrastructure, to be able to bring all of those pieces together. And recently we've expanded so that we can now use our cost map package to also look at considerations for not just pipelines, but also for rail and truck shipping. While we do spend our days looking, or at least I do, looking at solutions to the CO₂ transportation problem because it's so critical to the carbon management value chain, it does present a lot of challenges. A lot of what we'll talk about today is focused on pipeline because that's where the bulk of our transport capacity is going to come from. But some of the issues are also applicable to other modes of transit. And they span the spectrum from technical and economic to more regulatory and social concerns. And we'll touch a little bit on all of those. So one of the first major technical issues that you see when you talk about transporting CO₂ is that there's some really unique properties when you think about transporting CO₂ and CO₂ streams from emitters. The first is that typically, if you're transporting large quantities of CO₂ over large distances, you want to transport in dense phase, either as a dense liquid or as a supercritical fluid, in order to maximize your throughput in your pipeline. In order to do that, you pressurize the CO₂. So you have to be able to withstand high pressure. And typical operating pressures for those pipelines are higher than natural gas pipelines. With a CO₂ pipeline, you're looking anywhere in the 1,700 to 2,000, all the way up to 2,200 PSI, whereas for a natural gas pipeline, you're more around 1,400. So it's really a high pressure line, which as you're considering materials, flange selection, valve selection, you need to be mindful of pressure ratings and make sure you can withstand that high pressure. It is possible to transport at lower pressures in a gaseous phase. It's just less efficient to do so because of the reduced density of the CO₂ gas. Another issue is that during depressurization, so this could either be a depressurization in the event of a leak or a depressurization for, say, system shutdown and maintenance. If that depressurization occurs rapidly, the CO₂ can sublimate, form dry ice, and expose the system to very rapid cooling and very low temperatures. So you need to select materials that will be able to withstand being subjected potentially to extreme cold temperatures. One issue with CO₂ pipelines is because of that sublimation phenomena on depressurization, they're slightly more susceptible to fracture propagation because you maintain a higher pressure for longer in the event of a system depressurization. So you have to account for that in your design and make sure you're using materials that can withstand those pressures, making sure you incorporate things like crack arresters in order to prevent those long-running fractures. When you think about non-metallic components like gaskets in the system, many non-metallic materials can have CO₂ absorb into the material. And then in these depressurization situations, the rapid expansion of the gas can cause warping and damage to those materials. So you need to consider in selection of those non-metallic materials, materials that CO₂ won't migrate into to avoid that phenomenon. There's also issues related to corrosion because when CO₂ combines with impurities like water, it's highly corrosive. So it's important in the system design to make sure you're keeping the CO₂ gas dry. And more technical issues arise from the fact that these are not pure CO₂ streams in most cases. Different emitters will have different CO₂ trace components. Many pipelines will have a quality specification, and often those specifications will require something like 95% CO₂. But what's in the other 5% makes a difference on the performance of the pipeline. Things such as nitrogen can affect compression requirements for the system. Even small amounts of nitrogen can mean you need a lot more electricity to power a much greater pumping and compression to overcome the presence of that nitrogen. So consideration for those requirements in the design is important. We already discussed how water, if you don't keep your gas dry, you can have corrosion issues in your pipeline. And then some other components, like hydrogen sulfide, can be an issue in higher concentrations for permit condition compliance in the geologic storage wells, because if you have too many of those components, then you start to be considered a disposal well instead of a geologic CO₂ storage well. And there's different regulatory requirements you need to meet. So that this issue with both the presence of different elements from various sources itself, and also combining different sources and different CO₂ compositions in the same pipeline creates a significant design challenge for the system. One popular idea is repurposing existing lines, but for some of the reasons we already talked about, existing lines are often not rated for the pressures that you want to move CO₂ at in order to take advantage of the dense phase CO₂ for higher throughput. So a lot of times you'd have to transport as a gas, which can be okay, but if you're reducing the amount of CO₂ you can move, you're also increasing the cost per ton of CO₂ you're moving. It's really important to evaluate the condition, available records, maintenance histories on the system to look at, is the system really suitable for CO₂ service? Is it in good condition? What kind of upgrades are needed? Because depending on the condition and the original rating of the line and the CO₂ that you'll be moving through it, it can be cost prohibitive to convert. So it's just kind of a caution with that idea. Moving away from kind of the pure technical complications, design challenges can be overcome with careful consideration, with research, with new technologies, new materials development. But then there are other more regulatory and social issues. And one major challenge for pipelines is permitting. There's no federal authority for permitting. So permitting is done at the state and local level, which can be challenging to coordinate different requirements for different states with these interstate pipelines. And depending on the state and whether or not they have existing infrastructure from enhanced oil recovery, the permitting regimes and authorities may not be clear in the state. And part of your process may end up being for siting a pipeline to figure out or wait for or help the regulatory bodies in the state figure out how to permit a CO₂ pipeline. And then state and local jurisdictions, depending on the area, may introduce additional permitting requirements, and those may change frequently or Jurisdictions that didn't previously have requirements may add requirements. So that adds some kind of uncertainty and can add delays and risks into the project. Related to that issue, there are regulatory uncertainties from sources beyond just the permitting authority and the siting authority. One is in the space of safety regulations. In 2020, there was a CO₂ pipeline rupture in Satartia, Mississippi. And based on the findings from the investigation into that incident, as well as public feedback that the Department of Transportation, PHMSA, held after that investigation, some recommendations have come out from a lot of different organizations about what to do and what updates are needed in the regulation space. And the process of that is still ongoing. I had actually thought this webinar was going to be about the notice of proposed rulemaking, but the rulemaking has been delayed. And that creates uncertainty for projects because they don't know what new design changes may be coming down the pipeline with those regulations. There's some, you can get some idea about what might be coming, but it's not official yet. So that's that can potentially add costs to projects that are currently ongoing. Similarly, some local states and localities may take actions to restrict CCS activities. One example is in Illinois, there was recently a bill introduced to restrict storing CO₂ underneath of a particular aquifer. So movements like that can create challenges for ongoing and planned projects because an area that was previously thought to be a good candidate location may become banned by a particular state. And there may be extended delays in projects as legal challenges move through the court on that. In the financial space, a lot of uncertainty comes from the 45Q tax credits 12-year period. I think many people believe that the credits will be extended similar to how production tax credits and investment tax credits for wind and solar were extended, but there aren't currently announced plans, which makes projecting out the 20 to 50 year life of the project challenging from a financial perspective because that is a primary source of income for CCS projects at this time. And similarly, there's some uncertainty about capture and what facilities may end up capturing or not capturing CO₂, while ongoing EPA regulations about CO₂ emissions controls are contested in the courts. And all of this adds up to just more uncertainty, which can delay projects, can add costs to projects, and can deter investment in projects because of those risks. And then the last major thing is community engagement. It can really make or break a project. And we see that play out with, for example, the Heartland Greenway project was canceled. And in part, that cancellation was because of tremendous public backlash to that project. In response to that, you've seen a lot of industry initiatives about how to go about doing community engagement so that you don't create a situation where right off the bat, the communities around your project are adverse to the project. It's what we've learned from experiences like that are that it's really important to be proactive and early with your engagement and evaluate the environmental, the economic, the social impacts on the communities and the things that stakeholders around the projects really care about, listen to them and address those concerns for the communities around the projects. And then also deliver benefits to communities. It's really critical to this project success that the community feels invested and supportive of the project and feels like there's something in it for the community, that the community is going to derive benefit from that project. At Carbon Solutions, we do a lot of work in the community benefits space, and some of the innovative approaches that we've introduced are interactive community maps to get at this issue where different stakeholders care about different things. So we've created these interactive maps where people can turn on different layers, different points of interest. We can identify in our community engagement meetings things that people want to be able to see and look at and explore, and make that tool available so people can understand the project itself from perspectives that they care about. And then another tool that we have on the delivering benefits point is we've developed this local air quality emissions tracking atlas tool, which allows us to look at a community where these transportation projects and where these carbon capture and storage projects will be put into place so that we can evaluate what kinds of air quality and health co-benefits that these communities may experience because of the projects coming into their area. But it's the CO₂ transportation sector is really evolving, both to see the opportunities that are out there with the tremendous amount of growth that will be required in CO₂ transportation, and also to tackle some of the challenges that are out there in the transportation space. There's funding available through the DOE, both through its grant programs and through the Loan Programs Office for transportation projects to help get these larger interconnected CO₂ networks off the ground. The PHMSA CO₂ transportation rulemaking hopefully will issue a notice of proposed rulemaking in the coming weeks, months, that will add some clarity into the regulatory framework. There's attention on some of the issues that we talked about today in Congress. The Congressional Research Service has presented on many of these issues, particularly issues related to gaps in the safety regulations, the lack of a federal permitting authority for interstate pipelines, challenges with siting CO₂ pipeline projects, and getting those issues in front of Congress. The DOE is starting up a research development demonstration consortium to bring together industry stakeholders with the national labs, with the DOE, to bring together experts to really work on these problems together. And similarly, there's a number of initiatives out in the industry. For example, DNV, a major publisher of pipeline standards, has put out a guide on how to do community engagement for pipeline projects. So there's a lot of traction in the industry and in government to really help make these links between the sources and the sinks. And Carbon Solutions is really proud to be a part of it. We have 3 ongoing projects under the DOE BIL funded transportation projects. We have 2 pipeline feed studies, the Watch Pipeline in Wyoming and the Trail Chiefs Pipeline in Wyoming, North Dakota, and Montana. And we also have a Carbon Hub project in Wyoming looking at developing a CCS network in Wyoming to connect the full state as a statewide carbon hub, to look at how would we go about doing that? What would a blueprint for that look like? So we're really excited to be on the ground working on these. We also work on a lot of private projects in the space with just helping people figure out how they meet their needs to connect sources and sinks and fill in this missing transportation link. So we're really excited about that. And always happy to talk about our projects with any of you. So I will turn it back to Rachel to do Q&A.
Thank you, Tracy. I know I paused the chat there while we were going, but we did have a question come through, and our Q&A section is enabled if you want to drop any other questions in there. So let's see this first one. Okay. Pipelines, safest and cheapest transportation modality based on what underlying information? I feel like you kind of covered that, Tracy, but if you'd like to take it away, go ahead.
Sure, no worries. I had a chart pulled up earlier, just looking at some of the different costs and highlighting where the cheapest mode of the cost is. It's just generally quite expensive for large quantities to be able to get enough, say, rail cars and time on railroads in order to be able to transport and cost prohibitively so, as a specific example. On the safety records, the currently there's 5,000 miles of CO₂ pipeline actually in service in the US. And it actually has a quite good safety record. But the general statement is inferred from the operating history of natural gas and oil pipelines, where the accident incident rates are substantially lower on pipelines reported through the Department of Transportation than they are for transport of similar products via rail car or via truck. So it's based on accident data reported for similar product transportation.
Answer. Thank you, Tracy. Any other thoughts? Please take a minute to drop any other questions in the chat. We would love to answer them before we head out today. Right, we just got one more in the chat here. So how do CO₂ pipeline needs differ when we are sourcing CO₂ from DAC instead of CCS?
Sure. So when you're sourcing CO₂ from DAC versus sourcing from CCS, one thing is that typically in DAC, you are going to have a pure or close to pure CO₂ stream. So in particular, if you were to say build a pipeline to chain a bunch of DAC sources together, you could get around some of the issues in the pipeline design process that arise from other constituent components because you have that pure CO₂ stream. But if you're thinking about a situation where DAC is combined with other sources, you're going to be getting those impurities from some of the other sources. So then you don't really have a difference. In terms of planning, another thing that's different about DAC is the DAC facilities don't currently exist in many cases. In many cases, the project site hasn't been selected or finalized. So you have options in the transportation planning process to think about where the best place to optimize the trade-off between direct air capture needs and transportation needs and storage needs, and kind of select a location that will optimize your costs. We actually have a tool called Nectar that we use in order to help with that. Because similar to the situation with existing sources, it is not always the case that the location where you want to put a DAC facility and a location with favorable climate for DAC are not necessarily the same ones that have some quality storage locations nearby. But you can, because you're siting a new facility, you can look at that trade-off proactively and make decisions based on that.
Thanks, Tracy. We've got another audience question here in the chat. I can read it for you. Is there any cost model for transport and how that would play out in the entire CCS project? For example, the percent of the project cost. For example, one MTPA and 100 miles.
Sure. We have our own proprietary cost model. It's based off of Nettle National Labs cost models for CO₂ transportation. Those models are out there. We're not the only ones that have a model. The Nettle model isn't the only model out there. But in terms of playing out the cost of the entire CCS project, it depends a lot. Site-specific factors can heavily influence costs for the capture unit, the geology in the area and how deep you have to drill your well can vary and substantially influence that cost. And then depending on the area where you're routing your pipeline, land costs in the area, whether you're drilling through rock or through soil to lay the pipeline, whether you have to cross rivers, roads, all can influence the cost. So there isn't like a rule of thumb for I want to move one MTPA 100 miles, transportation will be X% of the cost. But it is possible for a specific project with like a little bit more information about where the project is, what the sources are, to come up with a quick number for something like that.
Okay, Tracy, we've got another one here. So what are the different properties or characteristics you look at when looking at rail, barge, ship versus pipeline?
So it's a little bit different because when you're thinking about shipping in non-pipeline means, for example, with rail cars, you have to consider losses over time from tanks. So that element of like time to transport and how long something's going to be moving on a ship or on a boat, because you have losses over time from tanks. That time element is something that you don't really have heavy consideration for in pipeline space. Similarly, scheduling issues with availability of a railway. That railway is moving people, it's moving cargo, it's moving coal. You have to compete for time on the railway. So that's a logistics element. If you build a CO₂ pipeline, it moves CO₂. If there's space for CO₂, you move your CO₂ on it. So you don't have that same competition for access to the railway element. And then similarly, the pressures and temperatures you're going to use for transporting and for storing via tank are just a little bit different. You're not going to use as high pressure. You're not going to you'll use dense phase liquid, but you won't be moving up to supercritical phase in a tank. And then other things you have to consider are really the infrastructure for loading and unloading CO₂ from wherever you're taking it and transferring it into the other transportation mode. And then when you get to a storage site, similarly unloading and ultimately getting it into, even if it's just like a short infield pipeline, to a pipeline that's going to take it to the well.
Right. Thank you for those answers, Tracy. Let's see if we have anything else here. Our last question. Thank you for presenting, Tracy, and thank you everyone for joining us. Again, check out our YouTube channel to see any of our previous webinars, and we will see you next time.